Hello, today's video we're talking about section 9.6, which is on the ratio and root tests. And so these are our last two tests for testing series for convergence or divergence. At the end of this section, I will also post a link to a document which has a summary of all of the tests for convergence or divergence, which you'll probably find very helpful. So let's get started. So the first test we're talking about is the ratio test. And so if we have an infinite series with non-zero terms, the ratio test says that that series will converge absolutely when the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is less than 1. The series diverges when that limit is greater than 1 or infinite. And then the ratio test is inconclusive when the limit as n goes to infinity of that absolute value of a sub n plus 1 over a sub n equals 1. And this is actually true for all p series, so you can't really use p series for the ratio or the root test because they'll always give you an inconclusive result. Okay, so just something to think about. All right, so let's do an example. So our first example is first of all, if you want to look up the proof for the ratio test, you can check it out in your book. So our first example says determine the convergence or divergence of the series from 0 to infinity of 2 to the n over n factorial. So my nth term is 2 to the n over n factorial. My n plus 1 term then would be 2 to the n plus 1 over n plus 1 factorial. So if I take the limit as n goes to infinity of a sub n plus 1 over a sub n, that's going to be the limit as n goes to infinity of 2 to the n plus 1 over n plus 1 factorial times n factorial over 2 to the n, right? Because I'm dividing, so just flip and multiply. And then I can go ahead and cancel a whole bunch of 2's. I'm going to cancel n 2's. So now I have the limit as n goes to infinity, and I have 2 on the numerator. And then this way I can cancel 1, 2, 3, 4, 5, 6, all the way up to n. So then I'm just left with an n plus 1. And so then that limit as n goes to infinity equals 0, which is less than 1. So I can say then that this is going to converge absolutely by the ratio test. So my series n equals 0 to infinity of 2 to the n over n factorial converges absolutely by the ratio test. All right, let's try another example. So here are two examples. Use the ratio test to see if they converge or diverge. So for example A, my nth term is going to be n squared times 2 to the n plus 1 over 3 to the n. My n plus 1 term then will be n plus 1 quantity squared times 2 to the n plus 2 over 3 to the n plus 1. So if I take the limit as n goes to infinity of the a sub n plus 1 over a sub n, I have n plus 1 squared times 2 to the n plus 2 over 3 to the n plus 1 times the reciprocal of the nth term, so 3 to the n squared times 2 to the n plus 1. All right, so now we're going to go through and do a whole bunch of canceling. So I can cancel n 3's, and I can cancel n plus 1 2's. So now I have the limit as n goes to infinity of n plus 1 quantity squared over n squared times, let's see here, so the 2's, there's one more 2 on the numerator and one more 3 on the denominator, times 2/3. So if I look at that first fraction, I have n squared over n squared, so, and there's no coefficient, so I know that that goes to 1. So my limit here is just 2/3, which is less than 1. So I can say that my series is going to converge absolutely by the ratio test. All right, so what I want you to do is I want you to pause the video, try example B on your own, and then press play. And I'm going to do it now. So for example B, I want to take the limit as n goes to infinity. And I'm not going to write out the n term and the n plus 1 term. I'm just going to go straight to taking that ratio. So the n plus 1 term would be n plus 1 to the n plus 1 power over n plus 1 factorial times, and then I want the reciprocal of the nth term, so n factorial over n to the n. And then here, I'm going to go through and cancel some stuff. So let's see what we can cancel. So if I look at my factorials, I can cancel 1, 2, 3, 4, 5, 6, 7, 8, all the way to n. So then I'm going to get n plus 1 to the n plus 1 over n to the n times 1 over n plus, wait, let's see here, n to the n. Where did I mess up? Oh, n plus 1. Oh, I see. I switched the denominators. That's why I'm confused. Let's keep the denominators where they are. Great. Okay, so once I do that, then I can see that I can cancel even further here. So right here, I can cancel a factor of n plus 1. Let me move this over. Okay, great. So now I have the limit as n goes to infinity of n plus 1 to the n, since I'm canceling one of them, over n to the n. And I don't need my absolute value anymore because n is always positive. And so then if I put all of this in parentheses to the power of n, I get n plus 1 over n all to the power of n. And then I can divide both of those terms on the numerator by n, so I get 1 plus 1 over n, all to the power of n. And this should look familiar to you as n goes to infinity. This limit, you should start to like figure out, oh, that looks familiar. What is it? It's in fact e, all right, which is greater than 1, so it diverges. All right, next, let's look at when the ratio test is not going to work for us. What does that look like? All right, so here's an example. So we want to figure out the convergence or divergence from 1 to infinity of the alternating series square root of n over n plus 1. So if I take my limit as n goes to infinity of my a sub n plus 1 term, so I don't need to, once I take the absolute value, I don't need to worry about that negative 1 to the n. So I'm just not going to worry about it because we're just worrying about the positive terms. So square root of n plus 1 over n plus 2 times n plus 1 over square root of n, right? So this is a sub n plus 1, and this is 1 over a sub n. So then if I go ahead and combine my roots together, I get the square root of n plus 1 over n, and then times n plus 1 over n plus 2, which if I look at both of those have a limit of 1, so I get 1 over 1, or 1 times 1, and so I can see that the ratio test is inconclusive. So that means you're going to have to use a different test, okay? And because we have an alternating series here, we could use the alternating series test. And that test will in fact give us a conclusion, and it tells us that it converges conditionally. So if you want to try that on your own, go ahead and verify that the alternating series test tells us that series converges conditionally. Okay, let's see here. Now we're moving on to the root test and some more examples. So the root test says that a infinite series converges absolutely when the limit as n goes to infinity of the nth root of the absolute value of a sub n is less than 1. And it diverges when that limit is greater than 1 or infinite. And once again, it's inconclusive when that limit equals 1. So let's take a look at an example and apply the root test to determine if this series from 1 to infinity of e to the 2n over n to the n converges or diverges. And so how you know you're going to use the root test is when you have an n in the exponent for both numerator and denominator. That's really going to be the key here. Okay, so let's take a look. So for this one, I want the limit as n goes to infinity of the nth root of the absolute value of a sub n. So that is going to be the limit as n goes to infinity of the nth root of e to the 2n over n to the n, which is going to be the limit as n goes to infinity of e squared over n. So my numerator there is just a constant. And so that's going to be 0, which is less than 1. So I can say that my series converges absolutely by the root test. All right, you can also do this series by the ratio test. It's just not as easy. So sometimes there are multiple tests that will work to determine whether a series converges or diverges, but there usually is one that will be the most efficient. And so that's going to be this one. This is not a geometric series because I have n in the base. All right, if that base in the denominator was a constant, then this could be a geometric series and that would be more efficient. But it's not. So I can't use geometric series for this one. I have to use a different test. So root or ratio would be great, and the root test works pretty quickly. All right, so here are some basic guidelines for testing a series for convergence or divergence. So the first thing to look for, because it's going to be your easiest test, is the nth term. Okay, so make sure that the nth term approaches 0. If not, you can stop moving forward, right? If it doesn't approach 0, then you know it diverges by the nth term test. The next one, is it special type? Do we have a geometric series, a p-series, a telescoping, or alternating? Each of those types of series have their own test, which is going to be the most efficient for you. And, or harmonic. Ooh, I'm going to add harmonic here. Is it special type? Harmonic. Harmonic, which, you know, fits into the p-series, but okay. Or I might even say, is it close? Maybe is it close to a special series? And for that, you would use one of the comparison tests. And then the next thing is to look at is the integral, root, or ratio tests. Oh yeah, and then can it be compared? So they're putting the comparison test last, but I would put, if it's really close to one of those special series, I might go straight to the comparison test before I would consider integral, root, or ratio. But if you look at it and you don't think the integral, root, or ratio test would be applied either, then go ahead and do a comparison test. Okay, so let's look at an example and go through these series and decide converge, diverge, and what tests we might use. So the first one, example A. So what I want you to do is pause the video, check these out, decide whether they converge or diverge and what test you would use, and then press play. Okay, so hopefully you have some ideas for each of these written down now. So the first one, if I look at this, it is, if I look at the ratio or the limit as n goes to infinity, I say the limit as n goes to infinity of a sub n equals 1/3, which does not equal 0. So this one diverges by the nth term test. Example B, we have a geometric series. And so Our base here, our ratio, is pi over 6, which is less than 1, so it converges. The next one, I don't have a special series. I have n and negative n squared. And so I kind of look at those and be like, well, the derivative of n squared is 2n. So I think I might be able to integrate this with some u substitution. So the integral test. And in fact, this one would converge if you do the integral test. Our next one, we have a general harmonic series. Remember, we can just compare to a p series here, and this one would diverge. For E, we have an alternating series, so I'm going to use the alternating series test. And remember, the two things for the alternating series is that the limit as n goes to infinity of a sub n, right? Ignoring the alternating part, so that's just this piece. And if I look at that, I get 3/4. Oh no, I get 0. And then if I also look at, is it decreasing? So a sub n plus 1 is less than or equal to a sub n. So therefore, this one is going to converge. F. So for F, if I look at this one, my numerator is a factorial and my denominator is 10 to the n. So this one actually, if I think about how fast factorials are growing compared to exponential functions, it's going to diverge. So this one diverges by the nth term test. Okay, my terms are not approaching 0 in that case. And then G is going to be something that I would use the root test on because all of it is being raised to the power of n. So if I do the root test, I take the limit as n goes to infinity of n plus 1 over 2n plus 1. I would add the absolute value, but I don't need them because it's always positive. And that's going to be 1/2, which is less than 1. So this one also converges. All right. Okay. I posted a summary of the series for you, all the tests for the series in Schoology. So take a look at that, and you might want to print a copy for yourself just to have handy. And that is the last video I am making for you for the school year. Oh, I'm so sad. All right. Well, thank you all.